We have Isabella Condotta with us. She'll be talking about smart grazing with iFarm University. And with that, Isabella, please take the lead.
Yes, thank you, Sala. So today I'll be talking a little bit about our research in this iFarm project and how we are integrating AI models into grazing management and our visions for the next steps. First of all, back up a little bit and explain some of our rationale and the why we decided to develop some of these components of the research. It all starts with the increase projected, the world population increase projected by 2050. We are projecting to have almost 10 billion people. And with that, we are expecting to have an increase in animal products consumption. With this increase for animal products consumption, we need to become more efficient. But we have to increase efficiency while still maintaining animal health, improving animal welfare, improving environmental sustainability, helping farmers taking care of their animals, and still keeping systems profitable. One of the ways of tackle these challenges would be using technology in the area of research and development that we call precision management of animals or precision livestock farming. I'll give you a brief introduction of what that is. The formal definition would be the management of individual animals by continuous automated and real-time monitoring of health, welfare, production, reproduction, and environmental impact. And how do we do this? This real-time monitoring, for that we have to have sensors. We'll start with sensors on the microenvironment of the animals, such as temperature sensors, humidity sensors. We can also know information about what type of food we're providing to an animal, maybe what type of housing, and analyzing animals' response to this environment. We can then create algorithms, and these algorithms will use input the environmental information, animal response to environment information, and then output decisions or alerts to a controller. This controller can be automated or it can be manual. And based on desired process outputs, such as how much an animal is gaining on weight, how much an animal is eating, how an animal is behaving, we can then make decisions on how to modify the environment or how to care for an animal in a specific way in order for us to obtain a different response from that animal. And then this feedback goes back to the controller and we can iterate over and over. So research in this area can happen in any part of the cycle. It could be research developing indexes that would be correlating behavior responses to environment. It could be research that develops algorithms or make algorithms more efficient to use that data and improve on the type of information we are getting. It could be research on these controllers and how they can modify the environment in more automated ways. So we really have a large area for research and can always have room for improvement on this kind of system. So that's when we start talking about developing tools and what it takes to develop tools for this kind of precision system. First, I'd like to talk about how you cannot manage what you can't measure. So it is important to be able to measure, as we saw, the environment and also animal response to that environment. And we need to do that by using sensors. We have a couple kinds of sensors. I like to group the sensors into wearables and non-wearables. So here I just brought an example of what kinds of sensors are out there and what they can do for us on the wearable realm. First, we have collars that provide information about animal activity, positioning, rumination, feeding time, and walking time. We may have ear tags that also can provide activity, positioning, temperature, rumination, feeding time. We may have nose bands that can give information about rumination. We may have tail rings that can also provide information about activity and contractions. We have leg straps, also for activity, lying time, walking time, and electronic bolus that can provide information about animal rumination. One thing to note about wearable sensors is that they may be more invasive. They are harder to keep up with if you have many sensors in one animal. So ideally, you wouldn't have multiple. You would pick one of those sensors that make the most sense for the production system that you have available. And oftentimes, they could be cost prohibitive depending on what kind of system you have. So those are some of the considerations. Most of them, you'll see that they also overlap on the data that they can provide. So it's not really smart to use multiple of the sensors to get similar information. Now, when we talk non-wearable sensors, besides the environmental sensors like temperature, humidity sensors, light sensors, you can also get sensors for monitoring the animals, such as cameras and microphones. And within the camera realm, we have different types of cameras. For example, here I have a thermal camera that can provide two kinds of streams, thermal images and color images. We have RGBD cameras that can provide, besides color images, they can also provide what we call depth images or 3D images that provide a volume or shape of the animal or the object that you're pointing to, and also night vision streams, which, as the name says, it provides you with images during the night hours. So your normal surveillance or digital camera can provide 3 streams: the color images or videos, grayscales, and the night vision as well, the infrared images. Those are not different from what cameras you would have, for example, in a house security system. And microphones can also provide us with sound. Some of these cameras may also provide you with sound, but this can be more directional and provide you with the sound of the animal themselves versus the sound of the environment. And this can provide some extra information, let's say cough information if you're looking for health status. So these streams, generally speaking, these cameras would provide you with information about behavior of animals and also physical characteristics of the animals. Behavior analysis you could do both with wearable and non-wearables. With cameras, you would really be looking at the animals and you could see what they are doing. With wearable sensors that contain accelerometers, for example, you would have to be predicting behaviors based on movement patterns of the animals. So there are pros and cons to both kind of sensors, and really depends on the kind of system you have. You would lean towards one or another type of sensor. This data that comes from sensors needs to be analyzed, and that's when we start talking a little bit about artificial intelligence or machine learning. Let's take a look on a quick definition of those terms. So artificial intelligence would be this broad group of techniques that will mimic aspects of the human intelligence. So when we are talking about robotics, we're mimicking humans' movements. If we're talking about natural language processing models, we are talking about the human's speech. If you talk about machine vision, you're mimicking humans' vision. And within this broad group of techniques, you will have a subset of that we call machine learning. And this subset really is about the algorithms behind those tasks. So these algorithms, they will improve, not based on continuous programming, but actually these algorithms will learn by themselves. And within this machine learning algorithms, we have one specific type of algorithm that uses neural networks, deep neural networks to function, and that's what we call the area that we call deep learning. And that's being widely used, especially for some of these computer vision tasks, to make our systems a little bit more efficient. So a quick difference between machine learning versus traditional programming. Traditional modeling would involve just this prediction step. So you have data. Let's say you have information on animal weight, and you want to predict milk yield, for example. You might have a equation that's your model, and you would provide data on animal body weight, and then the computer would use that equation with the data input and give you an output of milk yield, for example, predicted milk yield. That's simplifying the problem, but just to help visualize. Now, for the machine learning step, you would have this learning step before the prediction step. The prediction step is still the same. You have data, you have a model that could be an equation, and the computer would give you a result. But the difference is the model is not predetermined. The model is developed by the computer by providing sample data and expect results. So let's say I wanted to predict milk yield based on body weight. I would provide lots and lots of data on milk yield and expect and the sample data on the body weight, and then the computer would learn patterns between those two variables and develop a model, and then this model would be then used on the prediction step. So there's a learning component there, and that's what makes machine learning and not just traditional modeling. Now let's look into the examples of what we've been developing within the Farm of the Future testbed. The first module of what we are calling precision grazing is the feed intake prediction of the animals, and the second module will be animal monitoring. So this feed intake prediction has a few steps. We first want to predict intake per bite from animals. We also want to understand how many bites an animal takes, and then understand some crop characteristics at specific geographical locations in our field. And hopefully, if we have those components automated, we would be able to have an intake prediction plus a geographical location of the animals and combine that with the quality or crop characteristics of that specific location, and then finally get quantity and quality of ingested forage per animal. This first step of intake per bite estimation, we just started collecting data last week, so we are still in the process of developing, but pretty much what we are doing is recording animals as they eat. They ingest the grass and then count their bites based on the videos that we recorded. And we are also weighing this forage mass before and after it's ingested. We are also cleaning their rumen and trying to get the best estimate of intake per bite. Now, I do have some videos for this prediction of number of bites that an animal takes. This is just an example in two different stations. The one on the left is last year and our Farm of the Future test bed, or actually an adjacent location. We were just recording the animals. I don't know if you can see on this poles. Let me try to use a laser pointer. So here we have cameras all over. We're monitoring these animals as they ingest. This is just the corn stalks that we had left over. And we're just trying to understand how the sensors that the animals have correlate with the behaviors that the animals are performing. So we had accelerometer information on those animals. We had also microphones on them and GPS. So we are getting those streams of accelerometer, X, Y, and Z direction, and sound from microphone, and we are trying to correlate that with the different behaviors. So head up, head down, taking a bite, chewing, etc., etc. And we did something similar here. Let me go back to my arrow. We did something similar. This is a different location, obviously, with actual grass. This is location is at Embrapa in Brazil. And then we were doing the same, just recording the animals as they graze, manually annotating behaviors, head up, head down, taking bites, chewing, and they also had those accelerometers and microphones, so it can correlate those timestamps and ideally get a model that will be able to, only by using data stream from those wearable sensors, predict how many bites an animal is taking. So the next component here that I have some video is for the crop characteristics. We ran an experiment on summer to understand if we can get at first crop density and crop height. This is just an example of using a drone, a multispectral image drone. You can see that the more green the area is, like the grass on the background there, the redder the multispectral image shows, and the less green you have, actually the greener on the multispectral image. So we're developing models to correlate that with our types of grass. We also need forage height, and that's something that we wanted to compare manual methods versus an automated method. This is one of the methods that we are just starting to test. This is not my project. This is a project from Dr. Girish Chowdhury's lab, and they have some students there working on these robots that can potentially measure the height of the forage without really having to have a human going to the field and measuring it. So we would be sampling our field with that. This robot has what we call LiDAR sensor, so it measures the height and stops at a specific location there. So the other module of this, as I mentioned, is the animal monitoring component. And we first developed several models for indoor animals, and now we are trying to bring those models and adapt those models for outdoor applications. A few of the models that we've developed would be body weight prediction from images and body condition score, animal counting, animal identification, and I also didn't put here, but also gait assessment. So this is just an example of a video of how we collect data indoors. We collected the chute for these specific animals. This is on the laptop is the image from the cameras that we're collecting. The animal is over there. And you will see when the animals comes out, we get a full body view from that animal. And then that type of stream, camera stream on the left, we have a 3D image. On the right, we have a color image. That's an RGBD camera. We are using to develop models for weight prediction and body condition score prediction. This is just an example of using drones for animal detection and counting. We don't necessarily envision that we would use this all the time because drones are very tricky to use. They are highly dependent on environmental conditions. But it's just something that we were playing with. We really envision if we need to have cameras out in the field, we would have them possibly at a fixed location by the water, and then monitor the animals visually for the weight prediction, body condition score prediction models like that. So identification is very important, and for indoor animals, generally we would, if they have a wearable sensor, it would be easy to have ear tags or collars, but for grazing animals, oftentimes that's not the case. And correlating what you see, for example, on a camera with a wearable sensor, oftentimes is complicated. So we're playing with the idea of using identification from images. This is just a couple videos to compare what detection is versus identification. So you saw that drone video that was identifying cows on the video. that was just saying this is a cow, and this is what this video does, right? It finds the face of an image and it can detect the cow. Next step of this is actually identifying the animal. So after it finds the face, then now tries to give an ID to the animal. So this is the model working and identifying this cow as cow J050, for example. So this is just the breakdown of how this model works. We have an image that we collect with cameras. We have a model that detects the face, so just says this is the cow face. And then for training purposes of the model, we did blur those IDs from the tags, just so the computer wouldn't learn based on the tag and actually on the face of the animal. When we use this, we create a database of faces of animals and correlate that with ID and train an artificial intelligence model for ID. We ran that with 4 different breeds. A couple of these breeds are from our station in Embrapa in Brazil, a couple from here. Our hosting animals are not grazing animals. And then we are able to develop models that can identify these different breeds very well. This is another example of the data collection for weight prediction and body condition score. Let's take a look on what the analysis look like. So this is our 3D image from top view. When the animal comes out of the chute, then we process this image to just select the body of the animal. This is the head here. To the left, we've removed that region and create this 3D shape of the body of the animal. And with this 3D shape, we can predict body weight, and also based on some of the shape of the back of the animal, we can correlate with body condition score. Now for gait analysis, this is in conjunction with Dr. Josh McCain here at the University of Illinois. We are doing key point detections as the animal walks. This is an older version of this model. It has improved quite a bit. But we are really looking for specific points on the body of the animal, correlating that with gait, but also with conformation. So this video here has some angles that we are calculating as the animal walks. So angle of the steps as well. Finally, we have some outdoor, this indoor to outdoor transfer of technology. So how can we correlate the information that we get from the animals to whatever is happening in the field? This is just an example. We have this field where the animals, they are also, this is in Embrapa, they are in a plot where we have forest along with our crop. So the idea is to understand their behavior as it relates to preference for shade in this case. So once we have our GPS sensors on those animals, we can then correlate this with the location that they were and understand if that point in time there was shade or not, understand the sunlight patterns and correlate with their behavioral preference as well. So I spoke about how we are trying to put fixed cameras by water, but there's also an opportunity to use cameras on robots, and we are studying the possibility of using these little robots. Also, this is a Dr. Gray Chalderis group that's working with us. They're working with this robot dog. So the idea is using the fact that there exists herding robots, herding dogs, I'm sorry. Can we have herding robot dogs, and maybe if not herding, not for herding the animals, just to have this robots in the field collecting some information about both the environment and the animals. So there are 2 robots here. I'll play the video. One has a microphone, the other has cameras on it. And this was just a preliminary test to see if the animals would respond and how the animals would respond we have started these tests, and also to collect some sample data for the cameras and see what kind of view we get from the animals. But it's an interesting opportunity here as well. So how does this all come together? These are the sensors that we are going to test for data streams. We'll have wheeled robots, such as the robot that I showed that was measuring the height of the plant. We would have these robot dogs that will have GPS and the 3D cameras. We have collars on the animals that have GPS, accelerometers, speakers, and electrical shocker, and also they have microphone. I didn't include here. And these collars are kind of combo between a commercial virtual fence collar and our sensors. And then the UAVs, the drones, they're equipped with the cameras, GPS, and then the multispectral camera. The information that comes from the sensors, we are developing our models, and then they would be serve as input to our simulation engine. And then we have a component of this communication network that we're working with Deepak or Sish from the farms as well. This data would then fit into machine learning algorithms, and these models would then output a decision, or at least decisions that could be made by the human. So we're not really eliminating human from the process, just a decision support tool. And then the human could interact with this decision support tool also through maybe AI chatbots. And then a decision can be made in a way that we could automate potential rotation of the animals within the plot. So we would have maybe animal care decision to be made depending on what kind of behavior or physical information you got from your system, and also rotation decision, including when and where to move the animals based on your plot characteristics and their animal consumption, etc., etc. We could automate herding with robotic dogs if we see fit, and also we would adjust the virtual fence boundaries if we decide to use virtual fences. Some quick challenges and opportunities for this kind of research. Animals, they are complex organisms. They are CITD, complex, individually different type, variant, dynamic. Pretty much what that means is they have a personality, and the interaction of animals with technology is always hard to predict. So those are things that we have to take into account and really do lots and lots of tests to understand not only what is best on a technology standpoint, but also an animal technology interaction standpoint. Equipment, as I mentioned, is complicated. Cameras specifically are very hard for outdoor environments. This is just an example of the same type of camera, but different enclosures. This kind of camera is a camera that we use a lot indoors. When we go outdoors, we have to be creative. And I already talked about how we could mount cameras on robots, we could put cameras on drones, we could have cameras stationary. All of them have benefits and also have constraints. Collaboration is another area of opportunity and challenge. It's a very interdisciplinary area, so there needs to be communication between people from different backgrounds to make such a system work. Next, measure what's important and not make important what you can measure. It's very easy to be collecting lots of data. We need to do that in the beginning, collect lots of data, understand how this data correlate with each other and how different sensor streams correlate with each other. But in the end, we really need to understand what is actually extremely important, what it would be ideal to have, and maybe think of a more modular system in which you have your base system and then you could add things to it. You can imagine that data generation in this kind of system is very large. If we work with images, we produce almost 400,000 numbers for one image. Those numbers are the pixels of the images. if you're collecting 30 images per second on a video, you could get to 11 million numbers per second. And that would be almost 1 trillion numbers in a 24-hour period. And maybe what you just need is this one number animal weight. So how can we make our systems efficient that they are not really storing data as much, but actually transforming that data into useful information? So we need to be careful and try to be led by customers' actual needs. Our customers in this case of this project could be obviously are the farmers, but it could also be other researchers that could use such a system to produce more other types of information and other types of solutions for farmers as well. So we need to maybe have custom solutions depending on what kind of customer is going to be using that data. And just to finalize, ideally we want to have data integration. Animal data is processed at the cloud, provides information and advice for the animal caretakers, and outcomes we would have more efficiency, less working time, better work-life balance for our workers. And that's it. Hopefully it's an integrated system later in the line and integrates well with our crop research that's happening as well. Thank you.
Isabella, thank you so much for this.
Yeah.
It was a really, really informative talk. And we have already some questions, so I will ask some there. And then then afterwards, as we're waiting for more questions, I will give information on our programs and stuff like that.
Mm-hmm.
So this question is, in a sense, what you showed us is a lot of cool stuff. But what is the end goal? Why would we want to know the forage height or the number of bites a cow takes? What is the point of doing all of this precision modeling? Where are we going to end up from there?
Yeah, as I mentioned, it is a lot of data and a lot of information that you can get from your system. The end goal is to really develop a support system, as I showed, just to guide how the caretakers would care for the animals. So ideally, health issues would be at the forefront. If an animal is, for example, not ingesting or not eating as they should, or maybe they are not behaving as they should, those animals need to be taken care of. So that's one big concern, is health of animals. Another is just management of the animals within the farm. We're really thinking about this concept of precision rotational grazing. So can we have a better impact on the environment if we are more precise with our decisions for management? And that's what we are, the next step of this research, once we have some of this details figured out of how to monitor the animal's intake, monitor animal movement, etc., is what is the impact on the environment if we are more precise with our rotations, if we are more precise on how we consume forage. And in this specific case of the iFarm test bed, we are also trying to understand if it is even better for the environment, as we think, to do this rotation between crop, cover crop, and animal, or if it's just cover crop is better. So we have different treatments that we are also testing. So right now we are in a point that, yes, we are collecting probably more than we will need in the end, but we really want to understand the impact of the different components and what actually needs to be included on the final component.
So it sounds a bit kind of like how Gorilla Glass was invented before smartphones. So we kind of invented the technology before we figured out how we'll be able to use that technology. Would you say that's where you are at right now?
A little bit. We have different models and different things. And I feel like there's value on each model separately and each component separately. But I do envision that this would be more of a modular system and more tailored to each user specific needs. So if a person is really more interested on animal health, we would provide a module that maybe is just checking for the behavior and behavior patterns and understanding if an animal deviates from normal or not. Or if a person is really interested on intake, we would provide the module of intake prediction. Because obviously, if you keep adding things to it, it gets expensive. So I feel like the different modules would have value. The important part, it would be if I wanted to add more modules to the system, everything is integrated and works together if needed.
Okay. So let me introduce everybody to the programs, and then I'll get back to our questions and answers.
Mhm.
So if you want to move one more slide.
Yeah. This one?
Yes. So this is this program. In addition to being coordinated with FarmDoc, this is part of the iFarm University series. We do have a website at i-farm.illinois.edu that you could come and check some of the latest work that we have done. In addition, if you want to get updates to the latest programming that we do, sign up either using the QR code or go to go.illinois.edu/ifarm updates. And we'll add you to the mailing list and you'll get updates as they happen. Next slide. It's really important to thank all of the FarmDoc sponsors. This could not have happened without them. So we thank them all for their support. Next slide. And then also we give special thanks to our FarmDoc educational partners. Again, we could not have done this without them. You can go to the last slide. And this is our 2024 FarmDoc webinars. You could go to farmdocdaily.illinois.edu and you can see every single webinar we have conducted, either part of the iFarm University or even beyond that. And make sure to subscribe to the YouTube channel. Now, I do have another question for you.
Yeah.
So you've showed us how this system works on cows. If you had multi-animals, you had goats and sheep all together, could this system work at the same time and be able to differentiate between the animals and how they're being processed?
Yeah, I mean, if you decided to mix animals, obviously models developed for cows or cattle wouldn't necessarily work the same way for sheep or goat, but you would just have to fine tune those models. I personally work with other animals other than just cattle. I work with swine, I work with poultry and goats as well. So yes, all these models, they are applicable for different animals, but if we were envisioning a system where you would have multiple animals of different species together, then you would just have to fine tune your model to make sure that it first recognizes which animal it is, and then it knows which set of models you would be using for example, weight prediction or individual identification.
Okay. And my last question for you is that I know in plant world, there's this push to move from monocultures to polycultures. For example, our crop production to add cover crops or other crops that can be planted simultaneously, and there's a clear advantage for that. From an animal perspective, is there an advantage for moving from just one type of animal to multi-animal systems on the same farm, or does that bring more trouble than it's worth?
I don't know if I can answer that question properly, but my personal opinion is that definitely would. I mean, obviously there could be advantages, but I feel like that would be some concerns there. That would be complicated on how different species would be interacting with each other. I don't think it would be an easy task to do that.
Okay.
But yeah, I've seen some integrative systems. I think it would be easier to keep different animals, separated, but maybe have the integration of different crops and animals. And I'm not completely sure that you can do that in large scale in an easy way. There's gotta be, if we're going to move on that direction, there would need to be a strong shift in mindset and management and everything. I really think it's very different than what you're used to.
Well, thank you very much, Isabella. And thank you, everybody, for participating in this webinar. If you guys want to see this live on December 4th, we have a demonstration, and Isabella's team will be demonstrating some of these technologies. So come on, hop on over on campus at Stock Pavilion, and have a great evening. Thank you, guys.
Thank you.